Now I'm recording. Last we talked on Wednesday of last week, we were talking about the fundamental theorem of calculus, and we were talking about doing these definite integrals, but without using geometry. So we talked about using the antiderivatives that we learned about and the idea of indefinite integrals and mixing them together with the idea of definite integrals to evaluate a definite integral. And the main idea was, hey, if we're evaluating a definite integral, we can take the indefinite integral, forget about the constant, don't worry about the plus c on it, and then take your upper bound, plug it into the integral, take your lower bound, plug it in, and then it's upper bound minus lower bound. And we did a few examples of that. Now, I wanted to do a few more examples of that. Oh, you can't hear me? Can anybody else hear me? All right. So we're going to do a few more examples with definite integrals, and then we will be done with this section. And a little bit ahead, I don't know, maybe we can kind of get done a bit early today, and that'd be really nice if we could get done a bit early and just try to keep this a chill week. What I am thinking of doing for the homework, I'm thinking about just kind of combining this week's homework and next week's homework together to make like a larger assignment, and that way you wouldn't have anything due on Monday. That way you can kind of enjoy your Thanksgiving week as much as possible. So that's kind of what I'm thinking of doing, is just making next week's assignment a tiny bit bigger, so that you don't have a ton that you have to work on over the break. So anyways, yes, let's keep going. All right. So with integrals, if we have a quotient, we have to be careful because we can't just integrate the top and integrate the bottom. We have to deal with it as a whole. So it's much like derivatives, or you couldn't just take the derivative of the top and take the derivative of the bottom. So we're going to split this up to begin with. So I'm going to keep my bounds on here. This is x over 2x to the 1/3 minus x squared over 2x to the 1/3 dx. If we simplify that, this is 1/2 x to the 1 minus 2/3. 1 minus 1/3 is 2/3. Minus 1/2, 2 minus 1/3 is going to be 5/3. So I haven't done any integration yet. At this point, all I've done is just simplified it with algebra. This next step, I'm going to go ahead and actually, you know what I'm going to do before that? I noticed, so I could have done this ahead of time, but I didn't. I noticed both these have a 1/2 in them, so I'm just going to go ahead and pull that 1/2 out front so I don't have to deal with it. I mean, you have to deal with it, but just a little bit less. So the 1/2 will stay out front. Now I'm integrating. So I'm adding 1 to 2/3. That's going to give me 5/3, but it's going to be 1 over 5/3, so it flips the fraction upside down. So instead of writing 1 over 5/3, I like to be a little bit more efficient and just immediately go to 3/5. But as a note, this comes because you have 1 over 5/3. But you can just kind of go a little quicker that way. X to the 5/3 minus 5/3 plus 1 is going to be 8/3. So that'll be 3/8. 8x to the 8/3. And I'll make a note that this is because you have 1 over 8/3. And it's being evaluated from -8 to 1. Why is my... There we go. Screen has been a bit weird there. All right, so I'm first plugging in this top bound, 1. So 3/5 times 1 to the 5/3 minus 3/8 times 1 to the 8/3. And then I'm subtracting my lower bound being plugged in. Oh, there was a mistake in this problem. I'm just recognizing my notes have it. This should be a -1. And the reason that this has to be a -1, let me just point this out for you guys. It has to be a -1 here because if it goes through 0, this is actually undefined at 0. So just kind of come in here and put a negative. You don't have to change much. You just have to put a negative in front of all those ones. Put a negative in there. Sorry about that. That does have to be changed because otherwise it's actually not something we can find an answer to without Calculus 2 topics. So just make that a -1 and it fixes all of our problems. And now we're plugging in our lower bound, which is -8. So plugging in -8, we have 3/5 -8 to the 5/3 minus 3/8 -8 to the 8/3. And then, just kind of do the math a bit slowly. What I would like when you're doing this, I'm totally fine with you using your calculator to simplify some of this. I do want to see this step shown. I want to see you showing this step. But I'm okay if you then take this piece right here and plug it into your calculator. That's okay with me. This one should end up being -3/5 plus 3/8. Because it's being raised to the 8th power. But you can just use your calculator. It's no big deal if you want to do that. I say it's a little faster. And as long as you're showing that step that shows me you know how to actually plug in the number, that's what's most important to me. Okay. So I get -39/40 when I plug that in. Which must be, does this come out to be? Oh, sorry. This comes out to be, I had said this would become plus 3/8, but it's going to be -3/8 because I was thinking this guy right here, this will become a positive because 8/3, -1 to the 8/3 will be positive. Sorry, just had a moment there. So it ends up being -3/5 minus 3/8, which is -39/40 minus, and then you can plug this whole thing in on your calculator. Like I said, it just makes it a little easier and allows your calculator to do some of that heavy lifting. Which is what I am doing. And this number becomes -576/5. So simplifying the -39/40 minus a negative, so plus 576/5. 4569/40. This all comes out to 4569/80, but if you wanted to give a decimal answer, because the decimal does truncate, it does stop. This isn't even an approximate, this is a exactly equal. Both of these are exactly the same number. So this is not a rounded number I'm giving you here. This is the exact decimal expansion of this number. Is it tedious? Yes. The most tedious part is honestly this fraction bit, and that's why I'm saying if you can get to this step, I want you to show this step, but I'm totally fine with you using a calculator to go from here to here and here to here. I'm not ultra concerned with you showing the detailed fraction work of how you would get to negative 576. Can I answer any questions on that one? Okay. So let's go look at this next example. So we can go ahead and integrate right away with this guy. So the antiderivative, the integral of e to the x or e to the theta is just e to the theta. And then for secant squared, if you think of, oh, and somebody asked a question. So you only use plus c with indefinite integrals. Correct. Now, here's the thing. Technically, you could do a plus c here. So if I wanted to be real technical about it, I could put in a plus c right here. And I could put in a plus c right here. But notice what would happen if I put that plus c in, that this minus sign would get distributed to it. So you'd end up with c minus c, and they would just cancel out. So you technically could put the plus c in. It's just that they would end up disappearing in the very end if you had it here. Does that make sense? No problem. Yeah. So you can, if you really want to put it there. It's just that it will always cancel out. So by tradition, we just decide not to because it makes no sense to do it there when it's going to disappear anyways. So with indefinite, you have to, but with definite, it just becomes kind of a moot point. For the secant squared, the antiderivative of secant squared is going to be tangent. So this will be tan theta from 0 to pi over 4. So plugging in my top bound, I have e to the pi over 4 minus tangent of pi over 4 minus then my lower bound, e to the 0 minus tan of 0. E to the pi over 4 can't really be simplified anymore. Tangent of pi over 4 is 1. E to the 0 is 1, and tangent of 0 is 0. So really, the most we can simplify this, we can get e to the pi over 4 minus 2, because we could combine this negative 1 and the minus 1, and we get minus 2. And that would be our answer there. Can I answer any questions on those examples? I'm going to give you, let's see, which ones did I give you yesterday? Okay. I'm going to give you guys a few examples to try again, because this is all practice. Practice makes perfect on these. So let's go from 9 to 25 of t cubed minus the square root of t to the 5th plus 1 all over the square root of t dt. And we'll go ahead and do do that. All right. So go ahead and give these guys a try. I will tell you that you want to simplify these first before integrating. So you want to simplify first, then integrate. I'm gonna give you 5 minutes. I think that should be a good amount of time there. So I'm gonna pause the video, put on a 5-minute timer, and go ahead and try these ones out. All right, how are these ones coming along? Good, I think. Do we need a few more minutes, or are we ready to talk about them? Everybody? Getting messed up plugging it into the calculator. One thing that might help if you want to do it like really, really step by step. First of all, make sure you have parentheses. You could try plugging in just one little piece at a time. I will tell you that the numbers are going to be kind of nasty for this guy in particular. Both of them are going to have fraction numbers. But because I made this one up off the top of my head, this one will actually have pretty gross looking fractions. So if you're getting a gross looking fraction, it's probably correct, just a gross fraction. But we can look at this one and see if maybe you're getting the right answer. Just it looks bad. Let's see here. Move him down. Oh my goodness. There we go. All right. So you need to simplify this first one. When you've simplified, this will be t to the 5 halves minus t squared plus t to the negative 1/2 dt. So just so we are aware, this is t to the 5 halves. This is t to the 1/2. So 3 minus 1/2 is 5 halves. 5 halves minus 1/2 is 4 halves, which is just 2. And then 1 over the square root of t is going to be t to the negative 1/2. Integrating this, 5 halves plus 1 is 7 halves. So it'll be 2/7 t to the 7 halves minus 1/3 t cubed. Negative 1/2 plus 1 is positive 1/2. If you flip 1/2 upside down, that's just 2 over 1, which is 2. So this is 2t to the 1/2 from 9 to 25. Plugging in 25. So you have 2/7, 25 to the 7 halves, minus 1/3 times 25 cubed, plus 2 times 25 to the 1/2, minus, plugging in 9, that's 2/7, 9 to the 7 halves, minus 1/3, 9 cubed, plus 2 times 9 to the 1/2. You should be getting, it's a gross number, 359,585 over 21, minus, the other one comes out to be 2715 over 7, for a grand total of 351,440 over 21, which comes out to be, the decimal does stop. Unless, did I mess up my... Now I'm going to check a setting on my calculator to make sure that I didn't accidentally stop my calculator from giving me decimal expansions. No, this is right. So 16735.2381. Was that what you were getting on that one? I'm going to make this a little smaller so I have room for the other problem. Awesome. Excellent. Excellent. Yeah, so that one's it's just a kind of a gross one when you plug it in. For this next one, you're going to have to FOIL this one first. So if you FOIL this out, you'll get 4x squared plus 4x plus 1 dx. Integrating this, you'll get 4/3 x cubed plus 2x squared plus x from 2 to 4. Plugging in the top bound, so you have 4/3 times 4 cubed plus 2 times 4 squared plus 4 minus lower bound 4/3 times 2 cubed plus 2 times 2 squared plus 2. So this should give you 364 over 3 minus 62 over 3, which is 302 over 3. And this one doesn't come out to be the decimal doesn't stop, it doesn't truncate, so you have to just leave it in its fraction form. When in doubt, you can leave in fraction form. So if you were like, I don't know if I want to give this answer, when in doubt, leave it in fraction form. Any questions on either of those problems? Okay. So is it going pretty okay then for those ones? Okay, cool. Excellent. It just takes time to plug in, definitely. Definitely takes a little time to plug in. You get a bit faster though. You'll get faster with your plugging in. So here's the thing. This is a really interesting thing to go over, but if I'm thinking about the things that are necessary for you guys going into Calc 2, this topic, I'm going to skip this one. So we're skipping this page here. The things that are important, this stuff here is important. This is the generalization of the fundamental theorem of calculus part 1. I'm just going to skip it. If you really want to talk about it, you feel free to email me. I'm happy to talk to you about the generalization of the fundamental theorem of calculus part 1. But we have slightly more important things to cover, and that's what I'm going to cover. Yes, so question was, so is Calc 2 mostly just integration? And yes, you are doing a lot of integration. There's other stuff in there too, but there is a lot of integration. You're basically going to pick up exactly where this class leaves off. Some teachers, if you're lucky, will do a review of the end of Calc 1, so they'll review this material, but not all teachers will do that. And then you're going to pick up and just go more in depth in integration for most of the semester. So the skill of having good integration skills going into Calc 2 is incredibly important, just because that's what you spend most of Calc 2 doing. So more integrals is what we're going to talk about. The rest of the semester is just integrals from here on out. And there's not very much time left in the semester at this point. So besides this week, there's this week and next week, and then it is finals week. So next week is our last week of actual classes. It's gone by really quickly. I'm hoping to have stuff graded this week. I have a lot of exams that came in from the different classes I'm teaching. I'm hoping to have your exam 3s graded soon, so that you guys have enough time to get them done. Like I said, I think I'm going to make the next homework just kind of, I don't think I'm going to have anything due next Monday. I think I'll have it due the following Monday. And same with the exam redos. I think I'll just make that all due on the Monday of finals week. And I plan on putting out solution guides to exams 1, 2, and 3. Well, at least 1 and 2 prior to giving you the final exam, so that you're able to use that to study. I'll be able to give out the answers to exam 3 as soon as the exam 3 redos are turned in. So stuff to look forward to. Someone said, makes me sad I like this class. That makes me happy. I'm glad you enjoyed this class. And it's been a very interesting experience doing this online. And it hasn't been easy for, I think, anybody. I don't think any student thinks it's been the easiest thing. Learning calculus online and teaching calculus online definitely has been an experience, but I'm glad you enjoyed it. I'm very glad you enjoyed it. Oh, well, thank you very much. That makes me happy to hear. That's excellent news. That makes any of the tears that I've cried worth it. I wish that was a joke. That wasn't a joke. That's real. That was real. We're all having just a different time with this remote stuff. But I'm very, very happy that you guys have enjoyed this class. Just a little bit of the material left at this point. Like I said, we're going to get through this fundamental theorem of calculus stuff. Maybe we'll start the next section. But we're at the end. We're at the very end of material now. So, all right. So here's another, the fun thing. So we talked about area under the curve, right? We talked about how definite integrals talk about the area under the curve. But previously we were using geometry to figure out that area. But now we can kind of rephrase the questions so that it's asking us to solve a definite integral without saying, compute this definite integral. Oftentimes when I give a question like this on an exam, I say to set it up first, and you get points for setting it up, and then to compute it. Sometimes I just ask to set it up and I don't care about the computing. You see more of that in Calc 2 than in Calc 1, though. So anyways, if we have a problem that says use definite integrals to represent the area of the region bounded by the curves y equals 2 plus square root x, y equals 0, x equals 1, and x equals 9, then compute the integral or integrals. So I'm going to just draw a quick picture here. The square root of, or 2 plus the square root of x is a graph that looks like this. The line y equals 0 is this line right here. It's the x-axis. X equals 1. We'll put that right there. And x equals 9, we'll put right here. So the region bounded by these 4 curves, right? There's 1, 2, 3, 4. That's going to be this region right in here. So as a definite integral, this is going to go from 1 to 9, so lower bound 1, upper bound 9. And then the curve itself is 2 plus the square root of x. So this is this pink area This pink area is represented. The area of the pink stuff is the definite integral from 1 to 9 of 2 plus square root x dx. So now we don't need to use geometry. We can use all the skills that we've learned to make this work. So this will be 2 plus x to the 1/2, which we can then integrate. And because I think it's good to keep this practice in here, go ahead and compute the rest of this integral. I'm going to put in, hopefully this will be a quicker one. I'll put a 2.5-minute timer on. Compute the rest of this integral. If you finish early, start looking at the next problem, because I'm probably just going to give you time to try the next problem out, since the next problem is really directly related to this one. But I'll put 2.5 minutes on so you can finish this one. All right. What type of answers are we getting on this one? It should be a fraction answer. I hear 100 over 3. Anyone else? 100 over 3? $100 over 3 is what you should be getting for this one. So integrating it, you'd have 2x plus, this will become 2/3 x to the 3/2, evaluated from 1 to 9. Plugging in 1, we have 2 times 1 plus 2/3 times 1 to the 3/2 minus plugging in, by plugging in 1, I mean plugging in 9. Misread that top bound there. Plugging in 1, like how fancy I was in fixing that. Oops. Now I'm writing 9 where I should be writing 1. 2 times 1 plus 2/3 times 1 to the 3/2. This should give you 36 minus 8/3 for a total of 100 over 3. Oh, my internet on my computer went out. I hope that was just on my computer. So if you guys are chatting, I can't check. Give me a second. Okay. Can you guys hear me okay? Okay, excellent. Cool. So I am using Wi-Fi. So it's really interesting. My iPad doesn't seem to ever disconnect, but for whatever reason, my brand new PC will randomly disconnect for what appears to be no reason. If anyone has any suggestions for that, feel free to Canvas message me. A faulty Wi-Fi adapter. Would that be in the computer? Would that be something I'd have to send my computer out to get fixed? Sorry, hold on just a second. My husband just came in the room. Let me stop for a sec. Wait, can you close my... Thank you. Sorry. We dropped our dog off at the groomers today. I'm reading this suggestion. Let me stop the recording for a sec. And I promise I'll get back to the math now, but I would definitely appreciate help with figuring out that problem because it is quite annoying. All right. So what I am going to have you guys do is this next one on your own. It's the same looking process. The process looks basically identical. I'm going to give you 4 minutes to do it. I'm going to set a timer. Try this one out. I think you guys have it. I think you guys can do this one. All right. How is this one coming along? Good. I'm hearing goods. I like hearing goods. Why are you being difficult? There we go. So for this guy, we have y equals x squared plus 2. So that kind of roughly looks like this. Once again, it's bound by y equals 0, which is the x-axis, and then x equals 0 and x equals 3. So this is x equals 0. X equals 3 is roughly in this area. So we're looking at this guy here. The setup here is going to be from 0 to 3 of x squared plus 2. And then don't forget the dx. Don't forget the dx. Be careful with your notation. Don't get lazy. Double check everything. Integrating this, we're going to get 1/3 x cubed plus 2x from 0 to 3. When you plug in 3, you're going to have 1/3 times 3 cubed plus 2 times 3 minus the uninteresting case where you plug in 0 because that just comes out to be 0. But in either case, write it all down. So this should come out to be 15 minus 0, which gives you 15. How did that one go? Like now that you've seen the answer, how did that one go? Good, excellent. Faster than the first one. Got it right, so you're in a good mood. Those are all good things. Yeah, this one was a lot less nasty. This one had a lot less fractions. And someone asked about using x cubed over 3 instead. Totally fine. Yeah. So if what you had was x cubed over 3 instead of 1/3 x cubed, they are the same exact thing and you'll get the same exact answer. So whichever makes your heart most happy. All right, cool. Excellent. So let's move on to the next page then. All right. Oh, we put in a new example here. The notes got updated from the last time that I used them, so let's try this one. All right. Consider the region bounded by the curves y equals 2x plus 3, y equals 0, x equals 1, and x equals 4. Find a constant b such that the line x equals b splits the region into 2 parts of equal area, and then round your answer. So this is a fun one, actually. The line 2x plus 3 looks roughly like this. It has positive slope, it has a positive y-intercept, something like that. We're going from 1 to 4 here. So we're looking at this area here. And what's happening is we want to split this into 2 parts that are equal in area. So there's some number b between 1 and 4 such that this area here and this area over here are the same. Now, it can't be exactly in the middle of these two, right? Because this guy's going to end up with, if you put it right in the middle, this would have more area. But there is some letter b that is such that this area here is equal to this area here. So what we're going to do, I don't want to erase all of that. I just want to make this more blue. And I want to make this look more green. So that's our goal. Blue area equals green area. Blue area equals green area. Take a moment and think. Take a moment and think. Now, are there ways to do this geometrically? Maybe. Maybe. But let's not think geometrically. Let's think integrals here. We want the blue area to equal the green area, and we want our dog to not bark. But that's just not an option, is it? This blue area here could be represented with the integral from 1 to, we don't know what b is, but it's something, b, of 2x plus 3 dx. And the green area is going to go from b to 4, same line, 2x plus 3 dx. And we want those to be equal to one another. We want those to be equal to one another. Okay. So we can integrate both of these sides, right? So we have, this will be x squared plus 3x from 1 to b. On the other side, same thing, x squared plus 3x, but in this case from b to 4. So plugging in our bounds, we have b squared plus 3b minus 1 squared plus 3 times 1. On the other side, 4 squared plus 3 times 4 minus b squared plus 3b. So I get b squared plus 3b minus 1 plus 3 is 4, so this is minus 4, is equal to 16 plus 12 will be 28, minus b squared minus 3b. And we have two quadratic. We have a quadratic on one side and a quadratic on the other. If we move everything to one side, that is a quadratic we can solve for. And we can figure out what b needs to be by factoring it. So I'm adding b squared to both sides. I'm going to add 3b to both sides. And I'm going to subtract 28 from both sides. And that'll cancel out everything over here. So we have 2b squared plus 6b minus 32 is equal to 0. Factor out a 2. B squared plus 3b minus 16 equal to 0. All right. Is this one going to be a nice one? Minus 8 and 2. No, not 2. Not 4 and 4. So unless I'm mistaken, this is not going to be a nice number. Granted, my pregnant brain sometimes doesn't work so well, but I don't think this is going to be a nice number, which means we're going to have to use the quadratic formula. So x equals negative b plus or minus square root b squared minus 4ac all over 2a. So I get negative 3 plus or minus the square root of 73 all over 2. So that, of course, that comes out into two different ones. So if you do plus the square root of 73 over 2, negative 3 plus square root 73 over 2. I'm finding this, I'm figuring out what these values are because I need to decide which of these is between 1 and 4. Ideally, one of these will be between 1 and 4 and make our life better. So this is approximately 2.77. So that looks like a promising answer. Now this one should be a negative number because you are negative minus a positive. It's a negative on top, positive on bottom. But we'll put it in our calculator just for good measure. Oh, thank you. Negative 5.7. Thank you, Catherine. Negative 5.77. So this guy is a no-go. He is a no-go because B has to be between 1 and 4. So, giving an exact answer for B is equal to -3 plus the square root of 73 over 2. And you can check this with you can do like an approximation here. So, like I said, your calculator does have an integral button on it, and I'm okay with you guys using that to check your work. So if what you wanted to do here was looking at this very first one, if you wanted to check this for the blue area, I'm going to use the approximation, although you could use the exact number too. That would also work. But I'm going to use the approximation just to see if I get an answer that is close to what the green area is. So on my calculator, I am just going to do 2x plus 3 from 1 to 2.77. And I get 11.9829. For the green area, going from 2.77 to 4, my dog is going off. I'm getting 12.0171. Now, I know that I rounded this number. Here's the thing. I know that I rounded this number. So these are pretty close. And because I rounded and they're pretty close, I'm going to feel pretty good with that. And with your calculator, you can, I think your calculator will be okay with you doing really gross bounds. So if I put, I'm gonna see right now. Yeah. So if you do this exactly, if you instead of putting a rounded number here, if you actually put -3 plus square root 73 over 2, if you put that number in here, you will actually get exactly 12 for both of these. And there's that. So does that make sense on how, on the why of that, like why we would do that? Cool. Excellent. Excellent. All right. So let's talk about a new idea. It's not really a new idea, but a newish idea. So let's talk about absolute values and definite integrals. So if we're looking at an absolute value function, absolute values make things positive always. So if I'm asked to find the definite integral of an absolute value of a function, I'm going to look at this original function here. Here's my original function. I'm looking for what the absolute value graph looks like. Now, for this section here, the graph will look the same. Oops. This guy's what I'm looking at. But as soon as it goes underneath the graph, it actually ends up flipping itself out like this. So it actually flips and reverses itself for the graph of y equals absolute value. So anywhere that it would be underneath the x-axis, it is now on top and reflected. So it's like there's a mirror right here for the absolute value. So if I'm looking at the area from 0 to 5, clearly this graph isn't big enough for us to really show that. But I'm looking at this area here plus this area here. And normally when we take this integral, if we were using the non-absolute value, this would all be negative. But because this is an absolute value, we now want what was negative to become positive. So this guy right here is a problem area. So when you're doing absolute value, there's a step-by-step process instead. Your first step is you need to figure out where things are negative. So where the function becomes negative. And really what that's doing is finding out where the function crosses the x-axis, because that's where it's going to switch signs. So if we take 3 plus 2x plus or minus x squared and we set this equal to 0, we can factor this thing. I'm going to factor a negative out of it. So I have negative x squared, this would be minus 2x minus 3 equal to 0. So at x equals 3 and at x equals negative 1. And yes, this picture really showed that for us. But let's say we didn't know what the graph really looked like. We would need to figure this out. Oftentimes, you're going to want to make a sign chart to figure out where the negative areas are. So I want to look, and I'm going to make a sign chart to figure out where the original function before the absolute value was taken. I want to find out where that would have been negative so that I can accommodate for that when I set up my integrals. So I'm going to make a sign chart. I'm going to do negative 1 and 3. And there is this negative right here, so just make sure you're accounting for that everywhere. So I'll use negative 2, 0, and 4. Negative 2. So negative 2, oh my God, my dog. 3 negatives make a negative. 0 minus 3 is negative. 0 plus 1 is positive. My husband just brought our other dog home from the groomer. So now he is incredibly excited, which is adorable and incredibly annoying at the same time. All right. So we know what the positive and negative areas are. And we know that our particular integral is going from 0 to 5 of 3, absolute value 3 plus 2x minus x squared dx. So we're worried about starting at 0 going to 5. So it's really just, this is the problem area. 3 is the problem area for us because our integral doesn't involve anything lower than -1. So what we need to do for our next step is break it up into a positive piece and a negative piece. And then to counteract the fact that this will come out negative, we're going to flip the sign on it. We're going to make it a minus sign in front of it to counteract the negative. So sorry, we're running out of space here. So our original integral was from 0 to 5, absolute value 3 plus 2x minus x squared dx. What we're now going to do is we're going to split this into integral number 1, which was already positive. Integral 1 goes from 0 to 3. And we're just going to do the regular old function here. Then we're doing a minus sign. This is the counteracting the negative part. We're doing a minus sign, and integral number 2, which goes from 3 to 5, will be separate. And we can use the non-absolute value version because the absolute value is being taken care of by the fact that we're splitting this up. So the process of splitting this up into two different ones where you make the negative portion have a minus sign in front of it, that takes care of your absolute value. And now you're able to individually do these integrals. So here we're going to have 3x plus x squared minus 1/3 x cubed from 0 to 3 minus, same thing, 3x plus x squared minus 1/3 x cubed, but from 3 to 5. So plugging in 3 times 3 plus 3 squared minus 1/3 times 3 cubed minus, we know this is going to be 0, right? I'm just going to write 0. When you plug in 0 to all those x's, you're just going to get 0. Minus plugging in 5, 3 times 5 plus 5 squared minus 1/3, let's make that a better 3, 1/3 5 cubed, plugging in 3 times 3 plus 3 squared minus 1/3 times 3 cubed. So this bit right here, let's see, that's 18 minus 9, that should be 9. Hopefully. This piece right here is -5/3 minus, this piece should be 9. So what we have is essentially 9 minus, and then These are all in parentheses here. Combining together negative 5/3 minus 9, you get negative 32 over 3. I know it's kind of tedious on the math here. But 9 plus 32 over 3 is going to give you 59 over 3 as an answer there. So can you see here what happened? This blue integral, just like we said, the blue integral came out negative. The blue integral came out negative, but by putting this minus sign right here, because this minus sign just kind of followed all the way down, by putting this minus sign here, it took this blue integral and took it from a negative to a positive. So in the end, you ended up just taking the absolute value of just the negative area and adding it to the positive area of the positive area, and that's where that 59 over 3 comes from. Can I answer questions on that one? It's a process, but it really is just you find out where it's negative, and then you're going from there. You're splitting it up from there, putting negative, just splitting into two different integrals and then making the negative part positive. All right. We're going to do another example when we go to do this. We're going to talk about something new, but it involves absolute value. So it'll hopefully give you another practice to it. All right. So then the last physicsy thing that we talk about is displacement versus total distance. So when we're talking about these two ideas, displacement versus total distance, displacement is going to be how far you are from where you started. So if I started right here, and let's say I walked like 10 miles, but then I turned around and walked back 2 miles, and I stopped here, my displacement is the distance between where I started and where I stopped. So 8 miles. I'm 8 miles away from home. Even though I walked 12 miles, my displacement is 8 miles because that's how far I am from where I started. The idea of total distance, on the other hand, is just how much total distance did you travel. So again, if I start here and I go 10 miles, and then I turn around and I come back 2 miles, and I stop right here, my displacement is adding those two together. So I walked a total of 12 miles. Not my displacement, not my displacement, my total distance, total distance. My total distance is 12 miles. My displacement is how far I am from where I started. My total distance is going to be the total amount of distance that I have traveled. The difference between these two, and we go talk about what they mean mathematically. We talked about this relationship where if you have s of t, this was the position function. I know I've said this several times. And then if you took the derivative of the position function, you got the velocity function. And then we talked about in the opposite direction that the antiderivative of velocity was position. So you could kind of go this opposite direction here. And we said, oh, well, if you integrate velocity, you get position. But it goes a little bit further than that. If you're talking about indefinite integrals, this is true. If we're talking about indefinite integrals, this is true. But you can go a little further than that. If you integrate over a certain time interval, that'll tell you your displacement. Where's my pointer? That'll tell you your displacement from time A to time B. So from time A to time B, if you integrate velocity, that'll tell you how far from where you started you are based on time A and time B. Started at time A, ended at time B, how displaced you are. Whereas total distance, the total of distance you traveled from time A to time B is the integral of the absolute value of v of t dt. So when we talk about definite integrals, there's two different things we can talk about. We can talk about displacement. So sometimes we'll say net change, the net change. And total distance, which is how much was traveled, period. Does the difference between those two make sense? The difference between displacement and total distance makes sense? As my microphone had come out. Cool. Excellent. All right, so let's do a problem. So the velocity of an object measured in meters per second is given by v of t equals 4 minus t squared over 4. Find the displacement and total distance, traveled is spelled wrong, from times t equals 0 to t equals 6 seconds. So we'll start with displacement. So we're going from time 0 to time 6. And our velocity function is 4 minus t squared over 4 dt. So we can go ahead and we can just integrate that. So this is 4t minus, this will be 1/3 times t cubed over 4 from 0 to 6. I'm going to write that as 1/12, but you can write it however makes your heart happy. Plugging in the upper bound, we have 4 times 6 minus 1/12 times 6 cubed. Minus for the lower bound, it's going to be 0. So this should come out to be, I believe, 6. Let me just double check that though. So we have 6 minus 0, which is 6. And then we were told this is in meters per second. So 6 meters is our total displacement. Just flat out integrating it. Now, total distance, on the other hand, total distance requires us splitting up this integral because we're going to do the absolute value. So we're going to find out where this thing is equal to 0. 4 minus t squared over 4 equal to 0. If we want to do this without factoring, we can add the t squared over 4 to the other side, then multiply both sides by 4. You're going to get t equals plus or minus 4. If you're doing it this way, when you're setting up your sign chart, you're plugging back into this guy here. So I'm going to use x equals -5, x equals 0, and x equals 5. So really, you just have to do a little bit of math here. 4 minus -5 squared is 25. So 4 minus 25 over 4. 25 over 4 is 6.25. This is going to end up being negative. So if you do it this way without factoring, you have to actually plug it in. But this is going to come out to be a negative number. If you plug in 0, this is 4 minus 0 squared over 4, so that's positive. And if you plug in 5, that's why it's nice to have it factored, but you can do it without factoring. You have to plug it all in, negative. Our integral is going from 0 to 6, so 0 to 6. So we have two different integrals. We have one from 0 to 4, and this one is positive. And then we have a second one that goes from 4 to 6, and this one is negative. So I want you to set up and solve the rest of this absolute value. Using this information here, where it's positive, where it's negative, set up and solve the rest of this. I'm going to give you 4 minutes to do that. All right. Are we getting any answers for this one? Oh, yeah. Go ahead and finish it. The distance should be more than displacement, yes. And it's good that you are able to recognize that too. That's one of those mental steps that really helps you on tests to help say, okay, that doesn't make sense. This can't be right. Better try it again. I'm going to start kind of going through this one. So we know that the integral from 0 to 4 should be positive. And then because the next one will be negative, we're going to put a minus sign in front. So from 4 to 6, we are subtracting that because that should come out to be negative. So here we're going to have, it's going to be the same integral. It's going to be 4t minus 1 over 12 t cubed from 0 to 4 minus 4t minus 1 over 12 t cubed from 4 to 6. So plugging in 4 times 4 minus 1 over 12 times 4 cubed minus, it's going to be 0. We just know it's going to be 0 because when you plug in 0 to a polynomial, you get 0. So I'm going to be lazy there. Over here, 4 times 6 minus 1 over 12 times 6 cubed. Then plugging in 4, so 4 times 4 minus 1 over 12 times 4 cubed. So I think this one comes out to be, if I'm correct, 32 over 3. And the second one, altogether, once you do all of the math, comes out to negative 14 over 3, giving you a grand total of 46 over 3 meters. But if you want the exact breakdown here, let's see, this is 24 minus 1 over 12 times 6 cubed. So this guy comes out to be 6 minus 32 thirds. Which is where you get the negative 14 over 3. So the comment, it's because I plus everything into the absolute value equation and not the displacement. Oh, yes. So after you have found out where they change sign, then you can just get rid of the absolute value. You don't need the absolute value anymore. This negative right here takes care of the absolute value. It's an important point to make. I'm glad you brought that up. Yeah. So you'll get rid of the absolute value once you have split it up into the positive and negative pieces. Can I answer any questions on this problem? How did people feel like this problem went? Went well? I'll take went well. I'll take that. Somebody asked, how did I get minus 112? So that was what I did up here. So you have the t cubed over 4. Technically what you have is, it's like you have 1/4 t squared. So when you integrate him, the 1/4 is here, and then you have times 1/3 t cubed, which would give you that 1/12 t cubed. Does that make sense? No problem, no problem. Other questions? I really like having other physics problems over the semester since I have to take physics for, the calculus-based physics. It's good practice. I did not like physics. Granted, when I took calculus-based physics, I was taking it at the same time as calculus because my school allowed you to do that, which was an awful thing for them to. I have no idea why they allowed you to take calculus and calculus-based physics at the same time. Makes no sense in hindsight, but you'll be in much better shape than I was when I attempted physics, calculus-based physics, and calculus at the same time. So that's definitely good preparation for you. They'll change some things up and they'll make things more difficult, but having that foundation in mathematics will make you much stronger. So other than that, I think that is, I know it's 8 minutes early. I'm going to cut it 8 minutes early. That's what I'm going to do. Technically, we're going to have class on Wednesday. I'm going to be here teaching. I hate doing it on the Wednesday before Thanksgiving, but if you have to miss it, no big deal. It'll be recorded and posted just like normal. So no pressure if you can't make it. I am going to push the homework due dates back. I'll post an announcement about that. And by pushing them back, I mean, I'm basically going to skip one of our homeworks so that you guys can not worry about homework this week. And I'll have when the exam 3s are graded, I'll give a pretty generous amount of time for you to do the exam 3 redos. Yeah, so that is all I have for you. I hope you have a fantastic day. If I see you on Wednesday, I'll see you on Wednesday. Otherwise, have a good Thanksgiving and stay safe. Wash your hands. Wear a mask.